Welcome to Azal Engineering YouTube channel. I'm Engineer Kidana Mara. Today I will show you how to model, analysis, design and prepare detailed drawing for isolated or a single footing shown on the screen using the following data. Data from ETABS output looks like this. That is unfactored day load of 2,473 kilonewton and unfactored live load of 332 kilonewton. And data from the geotechnical or soil report looks like this. That is the bearing capacity of soil is 200 kilonewton per meter square, and the permissible settlement is 25 millimeter, and factor of safety is given as 3. Using this data, you can calculate very important data, that is soil subgrade modulus, which is equals to bearing capacity of soil, that is 200 kilonewton per meter square, times factor of safety, that is 3, divided by the level settlement, that is 25 millimeter. You must change this level settlement into meters. So finally you have to get soil subgrade modulus as this. After that, the other data that is given is the column cross section, that is for design of puncture looks like 500 millimeter by 700 millimeters to X and Y direction respectively. This shows that our column is not square, it's rectangular, so the footing must be rectangular to become more safe and economical. Watch this video up to the end, since the last point I have to tell you is a game changer. Subscribe my channel and share this video to structural engineers, site supervisors, contractors, civil engineering instructor and students, and finally to clients who need a structural design. Let's dive into this important design. First of all, how to open your safe software. So click on new model. New model initialization box is coming like this. From this, I have to select this, that is use built-in setting with to correct all data by yourself. So display unit, for the display units, it's better to use a metric SI unit. Regions for default material, it's better to use error code, but in our case, you can select any code based on your region or location. So in our case, it's better to use error code. Steel section database, actually it's not important because we are going to design reinforced concrete structure, but in case it's better to use error code also. Steel design code, that is a design code for your reinforcement bar, so it's better to use error code for 2004, and for that of concrete design code, it's better to use also error code. After that, make it okay. Our grid template is coming like this. After that, number of grid line in X direction, number of grid line Y direction. So for this reason, you have to use one grid pose in X and Y direction. After that, it's better to go to grid only and make it okay. You can use this template also, but in case to edit all things by yourself, it's better to use grid only. Make it okay. Our grid is coming like this. After that, it's better to go to define your material, your soil property, and all your load and load combination. After that, it's better to go to model your footing. So to define your material, go to define material property. After that, for concrete grade, it's better to use C30 as it is, because have defined my design code. Because of that, our C30 material property is similar with that I have select design code. So I have to use this C30 concrete property as it is, but in case of our rebar or reinforcement bar material, I have to change the grade. So to do this, it's better to go to modify. After that, I have to use array var of S500 grade. So our material type is array var. So the only case that I have to change is its modulus of elasticity. That is, I take this value from error code. After that, I have to modify some properties. That is modify our material property design data. So our material name is S500. That is good. So grade is also S500. So minimum yield strength, that is Fy. For a minimum yield strength Fy, I have to take grade of reinforcement divided by factor of safety, that is 500 divided by 1.15. I get this data, that is minimum yield strength Fy, which is equal to expected yield strength, that is Fy. So I have to copy this data to expected yield strength, that is Fya. A minimum tensile strength is Fu, which is the reinforcement grade by itself, and which is equals to expected tensile strength, that is Fua. So uh, I have to define our material of reinforcement grade as 500 like this. So make it okay. Uh, After this, I have defined all my material property. Then it's better to proceed to define section property. To do this, it's better to go to define also section property. After this, I have going to define both slab property or the footing part and that of the stiffened column, that is a column property. So to do this, it's better to go to section property, slab section. After that, I have to going to define my slab using this data. So modify property, that is slab or footing 700 with a footing depth of 700 for initial design trial. So modeling type, that is a shielding, make it a shielding. This is because footing thickness is greater than 300 millimeters, so I have to use a shielding. After that, property data, that is the type is slab, it's not slab, make it footing. After that, I have to provide the thickness, that is 700 for initial design trial. After this, make it okay. So our footing part is defined like this. From this data, it's better to use, or it's better to define your column and stiff. To do this, go to add a copy of property. So using this column and stiff, make it column and stiff, that is 700 millimeters. So the only have to change is make it the type to a stiff. After that, make it okay. So our section property and material properties defined like this. Make it okay. After this, it's better to go to define soil property. To do this, go to define spring property. Have to tell in the previous tutorial when we use point spring, line spring, and area spring. So you can go back to all my tutorials, that is for design of mats, detailing of mats, design of strap footing, design of combined footing. I will attach the links of this video in the description box also, so you can go back and check all this data. So in our case, it's better to use area spring. After that, add new property. So from here, I have to define your soil bearing as a name, that is the property name, your soil bearing capacity. Go back to your given data. From the geotechnical report, our bearing capacity of soil is 200 kilonewton per meter square. So I have to use a soil data name or a property name as soil 200. That is our bearing capacity of soil. So it is good. After that, you can add some note about the bearing capacity of soil or anything. After this, subgrade modulus, that is compression only. So you have to click compression only. So our calculated value of subgrade modulus is like this. So I will show. I have shown all the how to calculate this subgrade modulus before, so it's better to insert this value as a subgrade modulus. So after this, you have defined your soil property like this. Make it okay. So after this, I have defined all that data, but the rest one that I have to define is your load combination. You can define it after modeling. So you can proceed to model our footings. To do this, it's better to go to a quick draw area around the point. So first, it's better to select your property, that is footing 700 that we have defined first. So for initial design, it's better to go to use 3200 millimeter, that is 3.2 meter in X direction. This is because our column cross section in X direction is a minimum, that is 500, and in Y direction it's a maximum, that is 700. So I have to use a rectangular footing of 3060 millimeter, that is 3.6 meter, and I have to click on the center. So our footing is drawn automatically like this, that is a rectangular footing, which dimension, I will show the dimension. So go to draw dimension line. So our footing has a 3.2 meter in X direction and 3.6 meter in Y direction. So after this, it's better to go to draw your stiff column. So to do this, it's better to go to also kick draw area around that point. So I have to change the material property, that is column stiff. After that, our column in X direction has 500 millimeter, that is 50 centimeter, and 700 millimeter in Y direction. So click on the center. So our modeling looks like this. After this, the next point I have to do is defining the load combination and load pattern. After that, you have assigned the load to the center column. After that, the analysis, design, and detailing is done. So to define your loads and load pattern, load combination, it's better to go to define. So load pattern, I have to use as it is, that is tail load and live load with self-weight multiplier of 1 and 0 respectively. This is because the given data is as dead and live loads. So how to make it okay. After that, go to define. How to define your load combination, that is for a service load, and for the ultimate, the service load is for designing the cross section, and the ultimate load combination for the designs of reinforcement detail. I will show this later during the design and analysis period. So add a new combo. From this, it's better to combine combo and as a service. Combo and as a service. So have to add loaders, that is dead and live, as a scale factor of 1. So make it okay. After that, for the ultimate combination, I have to add a copy of this. So change this data to ultimate. Change this data to ultimate. After that, you have to add a self-weight multiplier or scale factor to be 1.35 for dead load, and 1.5 for a live load. This is because I have to use hero code. You can use your own building code of standard, and you have to use your self weight or scale factor for factored load combination for ultimate limit state design. So make it okay. After defining all the material property, all the soil property, section property, and all the load definition or the load pattern and load combination, it's better to proceed to assign the loads. To do this first, it's better to go to draw a joint object at the center of the column. This is to assign the load. So after that, you have to select your center of column. After that, go to assign. So joint load. After this force. So you have to assign the dead load. So our dead load to the global Z direction. That is the dead load is 2473. That is given from tabs output. So 2473. It's in kilonewton. You can add some property of movement. If you have a movement, you can add to this. That is in x and y direction. That may be to the negative or the positive direction. So you can add. At this point, don't miss that size of load for punching chair. You have to put your column and cross section here. If not, our punching chair design is not done. So for x direction, I have to provide the cross section like this. That is 500 millimeter and 700 millimeter. That is the cross section of your column given from the etaps output like this. After that, make it okay. So the dead load is done like this. Click again and have to assign your live load also. So in the same way, you have to change this as live. So the live load is 332 kilonewton. So I have to add 332 kilonewton to this footing. So all the load is assigned. After that, you have to assign your soil. To do this, click on the slab. So assign, have to use shell. After that, it's better to go to area spring. Select the soil data that you have to define before. Make it okay. After this, you can proceed to the analysis and design part. So go to analysis, run analysis and design. Before this, it's better to save your footing. So that is footing 2 or isolated footing 2 for tutorial purpose. So make it okay. The analysis is done like this. After this, it's better to go to check 3 basic pointers. That is the displacement, soil pressure, and the punching shear. So I have to check this data and compare to the given geotechnical data. After that, you can conclude to add some area or to add depths. So to do this, it's better to go to display. So show a deformed shape using the load combinations. That is for serviceability load combination. Make it okay. So our maximum deflection is 333.95. So it's beyond the level settlement, that is 25 millimeters. So you have to add some sections to this footing. So it's better to add some section, but the other data, that is go to display and you have to check your soil pressure. So our soil pressure for the serviceability load combination, that is it's beyond in thousands. That is beyond your given bearing capacity of soil. So it's better to add some section also. This is because our dead load is maximum, so you have to go to add some section, but before this it's better to go to check the punching shear, that is show a punching shear detail. Actually the depth is safe for in our case. Have to proceed to add sections. To do this it's better to unlock your model. After that click on slab. So you have to add, click on this point. After that, go to geometry. You have to add uh, 0.2 or 220 centimeter in both sides. So have to add 0.2 in both sides like this. So our slab can like this. So in four corner, it's better to add similar dimension. So make it okay. Our cross section is increased like this. So you must do this in both directions. If it is negative, you must put a negative to add or to get the total dimension. So after this it's negative, so have to add negative numbers. So our footing is increased like this. I will show the dimension. So go to dimension line. In x direction, it was 3.2 meters. So here in our case, it is 3.6, but in y direction, it is 3.6. So in our case, 4 meter. I will check this and add some data if it's not okay. So some cross section in depth if it's not okay. So I'm going to run analysis and design and check with the given geotechnical data as I do before. So analysis is finished like this. Go to display, show deformed shape using the load combination, that is serviceability load combo. So our deflection is decreased as 7.692, that is below the R level, that is 25 millimeters. So the depth that we have to increase is good. And the next one is you have to check your soil pressure. So using this service load combination, our soil pressure is 183.96, that is below 200 kilonewton per millimeter square, that is the given bearing capacity of soil. So our dimension or our cross section is good, but I'm going to check for punching shear, that is if it is necessary to increase depth or not. So our punching shear must be below 1. I have uploaded a video on all about punching shear, but in general for general knowledge, if your punching shear is greater than 1, the value of punching shear is greater than 1, you have to increase depth, but it's below 1, it's good. So but if it is actually 1, you are 100% economical and safe. So the to be safe and economical, our value of punching shear must be around 1, but it must be below 1. So you have to check your punching shear using this philosophy. So our punching shear is 0.817. It's actually below 1 and near to 1. So it's economical and safe. So our design of cross section is finished like this. So it's better to go to detailing of this isolated footing. So to do this, unlock your model, and first it's better to draw your design strips. This is because I have to use design strip method rather than finite element method. So to do this, I have to two choice. From these two choice, you can go to edit and add a design strip, but in our case, it's better to draw your design strips. So go to draw draw a design strip. So our design strip must be around the column. That is how to use a column and strip within a dimension of 500 from the center. So I have to correct this data to 500 to the center. So our design strip is A, that is along the X direction. So to draw this, it's better to go to snap option. So uh, to get a midpoint, so how get a midpoint? So I have to draw your column and strip to X direction, or column and strip or strip layer A like this. So in similar way, I have to draw for a Y direction, that is strip B. So I have to draw like this. We can show your or you can see your design strips like this. After that, it's better to go to analysis. So run analysis and design again. You have to get a maximum reinforcement area and the movement diagram. After that, you can calculate a spacing and number of reinforcement. I will show this in detail. So after this, go to display, show a slab design. After that, I have to use a strip-based method, that is show a rebar that is within a unit width, that may be a 1 meter design strip. After that, I have to go to both X and Y. I will show it independently. So right, make it okay. After that, you have to get a maximum area of reinforcement, that is the bottom reinforcement as like this. This is the bottom reinforcement. I have to take as a bottom reinforcement. This is because the movement is downward. I will show the movement. So you can divide this to any area of reinforcement, and you have to get total area of reinforcement and spacing of reinforcement. We will calculate it together on Excel sheet. So first, the software gives maximum top reinforcement as 1224, and that of bottom reinforcement as 123. You have to correct this data. This is because in case of isolated footing, you have to use or you have to check your moment diagram. So to do this, go to display. So forces during this, I have to correct or I have to use this. So our movement diagram is like this. It's at the bottom face. So maximum movement is at the bottom face. So you have to use the maximum reinforcement to the bottom. So from this, go to display also. After that, show a slab reinforcement. So in both X and Y direction, that means in layer A and B. So I have to get the maximum reinforcement, bottom reinforcement to X direction. That is 12, that is 1224.46. And in case of Y direction, that is 200. 2824.35. So you have to use this data, and you can get all the reinforcement details within a 1 meter strip. Go to Excel, and we can calculate all this data. So in case of Y direction, that is within a maximum area of reinforcement, that is 2824.35. 2824.35. That is a maximum area of reinforcement, which is AS. So it's better to use area of reinforcement that may be 14, 16, and 20 area of reinforcement, or there it's better to use so maximum area of reinforcement, that is in a Y direction, that is in Y direction. in y direction. I have area of reinforcement 200. We have area of reinforcement 2824.35 that I have taken from this data, and in x direction 1224.46. 1224.46. I will check it again. That is good. So this is area of reinforcement in x direction. So this is in y and this is in x direction. This is in y direction and this is in x direction. So have to go to calculate. Have to go to calculate all the area and all the total number and spacing of this data. So diameter of reinforcement is better to start from 40, 60 and 20 diameter of reinforcement. So for this diameter of reinforcement, area of reinforcement is for example pi, that is 3.14 times diameter square, that is 14 times 40 divided by 4 as a whole. So I have to close this number into bracket. So you have to get area of reinforcement for a diameter of 40 as like this. Drag this data and you have to only change diameter of reinforcement, that is 1/6. So you have to get all the area of reinforcement or area of reinforcement for each diameter of bar. So I have to change this as Tioni. This calculation is for 1 meter width. So in y direction, you have a total area of reinforcement, that is S 2824.35. So to get 1 meter width, it's better to go to divided this to area of reinforcement. That is it's better to take diameter of 200. So sorry, this divided by this data, you have to get total number of reinforcement for 1 meter for 1 meter width, that is 9 8.99 okay, 9 plus 1 which is 10. So you must add 1. So you have to get a diameter of for 1 meter width in y direction, you have to get a total number of reinforcement, that is 10. That is a total number of reinforcement 10 in with a diameter of reinforcement is 20. So I will cancel and I have to put that all the diameter or reinforcement to be like this. So it's better to check also in diameter of 60 also. So have to divide all this to divided by area of reinforcement, that is 60. So in case you have get 15 plus 1, that is 16 total area, total number of reinforcement in diameter of 60 for 1 meter width. I will check the spacing and provide one or select one from diameter of 60 and theory. So to do to get the spacing, it's better to go to divide 1000 to 10. That is total number of reinforcement. This is a 1 meter width. So you have to get 100 spacing, 100 millimeter spacing. But in case of 60 diameter of reinforcement, 1 meter width is divided by this total area of reinforcement, that is 62. It is below the recommended value, that is 75. So you have to take area of reinforcement, that is diameter of theory within 10 10 total number of bar in 1 meter width, that is 10. Or you have to provide your reinforcement as diameter of theory with spacing of 100 millimeters. So you can use this data, diameter of 20 with 100 millimeter spacing in y direction, that is the bottom reinforcement. But in case of x direction, it's better to calculate using like this. These were the most important point regarding to model analysis, design and detailing of isolated or single footing. I hope this video is helpful for you. Please like this video and subscribe my channel to get new updates daily. See you in the next important video. Thank you for watching.